Hello guys, welcome back to Maison African Motives, still on our engineering science and for revisions, working on the stress, strain and the Young's modulus in this case. Actually, we talked about this in passing to question papers and so forth, and you saw that it's just a direct application of formulas. All you're just gonna need are the formulas and also to understand your terms, which is important in simplification. So as you will see that this one is one of the easiest topics, is direct and straightforward. So make sure that you watch other videos so that at least you understand what exactly we are talking about here. All right, so question 7.1, we're not going to waste much time. We were given, in this case, a pillar that has a cross-sectional profile of. So whenever you're given this times this, or they can write 450 by 450. It's the area that you are given. So it means this pillar, it's in a form of a square because we are given the same units in this case. So it's in form of a square. So here we are obtaining side times side. So you are given area on that case. All right. Also, we are given the maximum compressive stress cannot exceed, meaning to say the maximum that we can have, it cannot exceed this. So meaning to say this is the maximum stress that you're given. So the question is calculate the maximum allowable load on the pillar. Definitely for us to have the maximum allowable, we must use the maximum value of the stress. All right, so that is the information that you're given. So like I said, you've got area, but these are millimeters. Convert to to meters so that you can have our area in square meters. In this case, just divide by 1,000. So our area will be given as 0.45 in meters. So it's 0.45 times 0.45. So that's gonna give us our area. All right, let us just leave it like that, or we can simplify, which is fine. But then the maximum stress in this case, so this is the stress at maximum, which is 5.5 megapascal in this case. All right. So the question is calculate the maximum allowable load, which is the force to be applied in this case. All right. Remember from our formula, like I said, this one is one of the direct, because even if you check on your formula sheet here, let's check what we are given and what we are not given. All right, I did not insert the formula sheet here. Let me just insert it quickly so that we can check one of the other things that are very, very important that we are given and what we are not given. All right, so from the stress here, we have got the formula for stress. These are the only formulas that we are given in our formula sheet. That is we can play around these formulas, and for stress and force and area, we can use this part that the stress is equal to the force over the area. So as we can see, we can manipulate that to make force to be the subject, since we understand that our stress is equivalent to the force over the area. So this is same as over 1. So you can cross multiply 1 times F. Then here we cross multiply 1 times the force, which is going to be the force is equal to the stress times the area in this case. All right. So that means we can manipulate our formula into what we want. And like I said, we are given the expression for area, which is side by side from the area of a rectangle that we are given. So that means we are simply going to substitute our values as we are given. So our force is going to be equal to the stress that you're given, 5.5 megapascal. That's 5.5 times 10 to the exponent of 6 times the area, which is 0.45 times 0.45. All right, so that is going to give us the required force in this case. If we were to calculate this, it was going to be all right, that's going to be 1,113,750 Newton. All right, so we can write this in kilonewton. That's gonna be 1,113,75 kilonewton, of which you can write in meganewton on this one, because as you can see, you can even divide by 10 to the exponent of 6. All right, but force just sounds good if you write it in kilonewton. All right, So that was it, 4 marks for that, just like that. All right, 7.2, we are given in this case a condition of a clevis type hook in this case. All right, so there we are given that the clevis will be attached to a rope that needs to lift up a load of 15 ton. That is the mass in this case that we are given to lift a certain mass of 15 ton. Remember, the mass is given as 1 ton is equal to 1,000 kilograms. So for a 15 ton, we're going to be 15 times 1,000. So we are given our mass in this case as 15,000 kilograms, which is 15 ton, all right? Then also the maximum shear stress if the pin, all right, the maximum shear stress if the pin is, or in the pin, not if, so in the pin, I was very surprised, okay, of 45 megapascal should not be exceeded. That is the, we are going to have this maximum stress again, just like the previous part. All right, so this is going to be our maximum stress of 45 megapascal in this case. All right, calculate the diameter of the pin suitable for the task. So we are asked to calculate the diameter that is suitable for the task in this case. So as you can see, guys, they're just repeating one and the same. Previously, we had the same condition here of given the force, and so that from the area, because it was a square, we do not have a diameter, it's going to be side times side. But this time, from this area, we are going to have a diameter because it's a circular part that we are dealing with. So it means we are just we are going back to the same formula that our stress is equivalent to the force over the area. So to have the diameter, we must have area. So we're going to just make the area the subject. That is, we're going to have F to find area, divide by the stress both sides. So area is going to be the force over the stress. And whilst the moment you calculate your area, why is it that we need the area? Because we understand the area is equivalent for a circular part is going to be pi d squared over 4. So you can calculate the diameter from there. Just make this the subject, cross multiply. That's going to be pi d squared is equal to 4 times a, which is 4a. So from this part, in order for us to have the diameter, just going to divide by pi both sides. So that means d squared is equal to 4a over pi. So to find d, introduce the square root both sides. So this is going to be the square root of 4a over pi. All right, everything under the square root. So this is going to be the formula that we are going to use to calculate our diameter if we have the area. So that's why I'm saying we can calculate the area, then we focus on the diameter later on. So our area, from the information that we are given, we do not have the force, but we've got the mass. Remember, I talked about this in the previous question, that the force is equivalent to mass times the gravitational acceleration, which is the weight actually that we are talking about in this case. All right, so just use the gravitational acceleration in that case. So meaning to say, in place of this, we're going to substitute mass times gravitational acceleration. So our area is going to be the mass of 15,000. So you're going to have 15,000 times the gravitational acceleration of 9,8. We now have the force that is required over the stress, the maximum stress of 45 megapascal. So that's 45 times 10 to the exponent of 6. We are going to obtain an area from there. So that was going to be 0, something like that. Okay, let me just write it here so that we can properly see the answer and we can play around that answer in a way that we want. All right, so from our calculator here, gonna have 15,000 multiplied to 9,8. So that's 9,8 over 45 times 10 to the exponent of 6. So that's 10 to the exponent of 6. So this is what we're going to have 0, 3, something like that, 3,266, something like that. Okay, so it's going to be 3,266 like that. Okay, 3,266, something like that. All right, something like that, times 10 to the exponent of -3. All right, so this is times 10 to the exponent of -3 in square meters. All right, so with this area, we are just going to find our diameter. Remember, I said diameter is the square root of 4a over pi in this case. All right, so from this formula, we can calculate our diameter in this case. So that's our diameter, therefore, is going to be the square root, remember, of 4a over pi. All right, so you're going to substitute. That will be the square root of 4 times the area, which we got here, 3,267. Just going to round off here. It's going to be a 7. Remember, it was 6, 6, and so on. All right, times 10 to the exponent of -3 over pi in this case. All right, so that's will be our diameter. So let us just have our calculator again so that we can calculate. So it's either you can use this as it is, or you can just substitute this one that we now have. So that's 4 times 3,67. So 267. All right, that's 267 times 10 to the exponent of -3, like this. All right, over pi in this case. All right, so this is over pi. So that will be 0,06449, which is going to be 0,064 in this case, or you can write as 645. All right, it's up to you on this one. So it's going to be 0,064 in meters, all right, to 3 decimal place as per the instruction of our question paper. Or like I said, you can even write to 3 significant figures, having a 5, which is fine. But that is how we're supposed to calculate our diameter. Remember, we have got the mass, so we're going to have the force from there. You calculate your area, then from the area, just make the diameter the subject. So these are the questions. They just want to play around with you guys. They just want to play around with you. As you can see, these people, they are good at that. So be careful when answering. Take the information down. That's the best way. All right, 7.3, we've got a tensile force is applied. A tensile force of 85 kilonewton is applied to a copper conductor. We are dealing with a copper conductor, causing a stress of 30 megapascal. The original length is, and the Young's modulus of copper for copper is 117 gigapascal. Calculate the diameter of the rod. We are back to the same thing, guys. These people, this question paper, I don't know. It was just a repetition if you check. The diameter again. All right, anyways, let us take our information. We're given the tensile force. That's we've got the force in this case of 85 kilonewton for a diameter, having a stress in this case of 30 megapascal. The original length of the copper is being 4 meters. Then the Young's modulus in this case is being given as 117 gigapascal. Calculate the diameter of the what? Of the rod. So just like the previous question, this one is just a repetition. The diameter suitable. We have to calculate the area, then we use the formula for the diameter from that area. It is the same concept because these are the same values that we have in, because here the only thing that we have here is that we do not we are not given the mass, we are given direct the force. So it's just a repetition from the last question. So as we saw from the last question that we said, we ended up having area is the formula for area is force over the stress. So area, after making this the subject, area is going to be force over stress in this case. All right, so our area is going to be the force of 85 times 10 to the exponent of 3 over the stress of 30 times 10 to the exponent of 6. All right, so that was going to give us area in this case, just like the previous part. It was going to be 0,00283 if you round off properly in square meters. Then in order for us to have the diameter, we are going to have our formula. Remember, diameter is the square root of 4a over pi. So meaning to say from here, we are going to calculate our diameter in this case, right? Knowing that the diameter is equal to the square root of 4a over pi. So just a substitution that you're going to have, which is the square root of 4 times the area, 0,00283 over pi in this case, all right? So that was going to give us the diameter in meters, since this area is in square meters. So the diameter was going to give us something like 0,06 in meters, or 60 millimeters. If you want to convert to millimeters, it's your choice. It's up to you. All right, so as you can see, this whole question was a repetition. Then calculate the strain again, we are given the formula of our strain. Remember, we've got the change in length that we have got the length that we are given, and but in that case, we cannot apply it. But let us check here. We're supposed to actually use the original length over the change in length. We do not have the change in length in this case, so it's going to be difficult for us to use that length that we are given. All right, but if we check on this formula from the Young's modulus, we are given the stress over the strain, so we can use this because we have the stress, we have the Young's modulus. So the second one was going to be the best because we do not have the change in length. If we're having the change in length, we're going to use that because we have got the original length, but we do not have the change in length. That is the only part that limited us to use the first formula that we saw for what? For strain. Otherwise, it could have we could have applied that if we were given the change in length. So therefore, it's not possible. So we saw that the Young's modulus is equivalent to the stress over the strain. And we are supposed to calculate the strain in this case. Remember, our question is to calculate the strain. So let us make the strain the subject. Just gonna cross multiply here. That will be the Young's modulus times the strain is equal to the stress. So to find the strain, divide by the Young's modulus both sides. In this case, this will give us the strain is equal to the stress over the Young's modulus. And we have everything here, the stress being 30 megapascal, which is 30 times 10 to the exponent of 6 for megapascal, then gigapascal to the exponent of 9. So this is going to be over 117 times 10 to the exponent of 9. So take note, these are Pascal, so they'll definitely cancel. And so the strain does not have the units at the end. So the strain here is going to give us that was actually from your calculator, it's going to be 2,56, something like that, 4 times 10 to the exponent of negative 3. So that's a 4 times 10 to the exponent of negative 4, right? And we do not have the units. Or as a decimal, if you wanted, it was going to be 0,000256 or something like that, all right? So as you can see, it's best just to write it as an exponent like this, 2,564 times 10 to the exponent of what? Negative 4. So that is how we're supposed to attempt this question. So as you can see, guys, this is one of the easiest topics. The only part that you have to play around, I want you to check the question paper. I think so supposed to be November 2022 or November 2020. Please revise that question paper. I think that is where we have a lot of things that we considered more than this question that we are having. So also, you are supposed to know your formulas. Like I said, these are the formulas that we have, and also to play around this formula, which consists of the force, the length, the area, and the extension that we the length that we are given, the length, which is our extension, and the original length that we are given. So it's something that you need to play around and use your formulas where they are applicable. So these are the only formulas that you're going to be having from your formula sheet, and learn to play around these formulas in order to answer any question that you are given.